Okay, I hope it is recording. It is recording. All right. So, yeah, welcome to this course, everyone. Those who have joined and those who are about to join. So, I'll be this first 5 minutes. I'll be simply introducing. So, those of you who have friends who are also doing this course, please invite them to join the session. So, yeah. So, without any further ado, so my name is Mayank Anupam, and this course name is, as you all know, you are doing it. So, it is Analog IC Design. This is a NPTEL Massive Open Online course or MOOC course for short, and it is being conducted by IIT Madras, right? So Professor Sankaran Aniruddhan and Professor Nagendra Krishnapur are jointly taking this course, and so basically and my job here is to hold these tutorial sessions. Okay, so these sessions which I'll be starting from today, this will be going on for 12 weeks, and it will be held this will be a weekly session. So basically there will be one session per week, and it will be going on till the end of this course. So 12 weeks are given for this course, and we'll have 12 sessions in total. All right. So, so the purpose of these sessions here is to simply not. It is not for me to simply come here and then lecture, right? So the purpose of these sessions is for you to interact with me, right? So basically, this is an online course. So the advantage of the advantage of sorry, this is an online course, so that is why the professor will not be able to interact with you, right? You will not have that interaction benefit or advantage here. So to counter that problem, we are here, right? We are here to make sure that you are able to talk to us, you are able to clarify your doubts with us, okay? And we also form kind of an intermediary between you and the professor, okay? So since in this course I'll be the only one who will be holding this session, so yeah, I'll be acting like an intermediary between you and the professor. So whatever doubts you have, you can ask me. I'll try to clarify those in the sessions that I'll be holding on Mondays. Okay, so the sessions will always be on Mondays, uh, unless there is some other commitments that I have. Then they will be announced to you before only. Okay. So if somehow if because of some reason I'm not able to conduct a session on Monday, it will be postponed or preponed to another day. Okay, and that notification will be coming to you beforehand. Don't worry about that. So yeah, I think people have few people have joined again. Let's I'll be simply starting now. So let me share the screen. Shit. Okay. Yes. Is the screen visible? Good. All right. Okay. Okay. Fine. So yes. 1 second. Yes. So again, reintroducing myself for those who have joined later. So this course name is Analog IC Design. It's an NPTEL MOOC course or massive open online course, which is jointly conducted by Professor Sankaran Aniruddhan and Professor Nagendra Krishnapura from IIT Madras. Okay, myself, I am the tutor for this course. These are the sessions. I mean, these tutorial sessions which will be held weekly on Mondays. I'll be conducting them. I am a PhD scholar in the Department of Electrical Engineering at IIT Kanpur. All right. So, without any further ado, so let me just quickly go through the key points that were discussed in the first week. So this was the key points are given here. Key topics are given here. First one was the concept of negative feedback control was introduced to you. So what is a negative feedback control? Something like that you were taught about, and then you were also taught what is what is the point of making a negative feedback amplifier, and how can we make a negative feedback amplifier, right? After that, once we got into how to make negative feedback amplifier, we saw something like we saw that it actually behaves like a first order uh, circuit, right? A circuit which has one pole, and that is why we talked about its step response and its sinusoidal steady state response. We also talked about a little bit about what is loop gain, what is loop gain frequency, and then we saw a little bit about what is an op amp and what how can we make use of an op amp, right? I also went through some of the questions that were that was posted in the first assignment of week one. So in that there was something called as power delivered. So I will also talk about I'll also talk a little bit about how can you find out power delivered, since a lot of people have a lot of doubts. I mean, over the years I've seen that a lot of people have doubts in following passive sign conventions. So something that is very important whenever you want to find out power delivered. We always talk about passive sign convention when we want to find out the power delivered or power consumed in a circuit. So I'll be talking. So these are the rough points which I'll be covering today. And after that, I have some problems for you. Okay, so many problems. So I will not be discussing all of them. I'll be discussing a few of these, and the remaining ones will be for you to solve yourself. Okay, you can ask me in the later sessions, or maybe in the next session, if you have any doubt. All right. So any doubt till now with the flow of the this thing, basically the flow of the session, or the objective of the session, or the motivation of the session? Any doubts? Any doubts regarding the modality? Before I proceed with the this course, I would like you to ask me anything that you have in mind. Any doubts regarding the what I mean, what are you doing in this course, or what is the importance of this course, or anything like that? By the way, I assume that all of you who are doing this course have a good understanding of the basic circuit theory, right? I mean that is the foundation upon which this course is built upon, right? So I assume that all of you have a very good understanding of basic circuit theory, because that I'll be taking for granted at times. All right. Uh, Again, to emphasize, again, I'll like to re-emphasize that this course is not supposed to be these sessions are not supposed to be just for me talking. Okay, it is supposed to be an interactive session where you have to talk to me also. If it is just me who is talking, there is no point, right? I can as well simply put a recording, and I will not even come to this session. So you have to constantly ask me questions if you have, and you have to make this session interactive. All right, so Ravi Singh, you have a question? You have raised your hand.
Yes, hi.
Hi.
So it has been quite for some time for me, like having done these courses. So, in case of the circuit theory being used anywhere, like rigorously, I mean, it's just a request. It would be great if you could like provide a source for it, maybe from where, if we have doubt, we can like go and refer to it.
I could not quite catch your question because there was some noise at the background. Could you please repeat that?
Yeah, sure, no worries. So I was saying that I mean, at certain points we would have very rigorous circuit analysis,
Yes.
um, and it has been. I mean, personally for me, it has been quite some time since I have done this.
Okay.
So I mean, could you please also like provide a reference if we feel in case I mean we are having like it's quite rigorous, so a reference for like where we can go and refer to it.
Sure.
Maybe.
Sure. Sure. Definitely. Anything else?
No, that's it. Thank you.
Okay. So before starting, so let me just mention the reference for this course. I'm pretty sure the reference was given in the course handout also, wasn't it?
It was, yes, one of the books. Yes.
Let's also, so maybe I'll just put it here or the reference. Okay, so the reference for this course would be, so one the reference will be again, needless to say, you all must have heard this. So the first one, doubt, no doubt here, it is analog, yes, CMOS integrated circuits, I think. Uh, you have heard this book? Have you seen this book? Hmm? Have you ever heard of this book or this author, Razavi, Behzad Razavi? Okay, okay,
Uh,
fine. So this is one
since
of the courses. This is one of the books. Okay, Behzad Razavi. He's a professor in UCLA, University of California, Los Angeles. Okay, so his book is the most famous one, which I think should be enough for you to understand, build up the understanding. Okay. However, not the whole book is going to be, I mean, covered in this particular this thing lecture series. I think uh, you will be able to understand if you see the look at the topics, okay, look at the contents, you will be able to identify clearly which of the topics is being you have to refer to. Okay, since I mean, let's say for example, this week we are talking about negative feedback, right? So there is a whole chapter devoted to negative feedback in the book, in this particular book. Okay, so other than that, and you will also find a lot of questions, by the way, to solve. So they are also very good questions. There are a lot of solved examples, which uh, which are very good actually, by the way. So the solved examples are very good, really good. They are supposed to mean something. I mean, these are not just some example cooked up to make your life difficult. Okay, the examples which are given in this particular book are actually real world examples. Okay, so please try to solve them and go through them diligently. You'll be able to get a lot. I think this book should be more than enough for you to understand the whole course. Okay, and if you want to do something some more, so you can always go back and refer to the ICS website. Okay, ICS website of, so it is a website from site of IIT Madras itself. Okay, so they have a lot of at this website you'll find a lot of materials. Okay, I think I hope you have all at some point of time gone through this website. This has a lot of content. Okay, this is a lot of assignments, lot of lecture series. Okay, and you will be able to get a lot of information from this website. This also has a lot of I mean, Professor Nagendra Krishnapura, his personal website has a this thing, has some design library, PDK also. PDK is short for Process Development Kit. It is something which contains the information of MOSFETs and all. Okay, so I mean, this is to simulate. These things are needed for simulation purposes. You can, if you go on the website, you will be able to understand. So there are a lot of things which you can possibly explore. Okay, so but for the purpose of only building up the understanding, this book is enough. Okay. If you want to do some simulation assignments and all, you can maybe check out this website. Also, check out the website of Professor Nagendra Krishnapura. So I'll just mention it. Uh, okay, I think this should be more than sufficient for your purpose. Yeah. So anything else for anyone? I mean, any other doubt?
Hello, am I audible?
Yes, Raghav, you are audible. I hope your
I
name is
joined.
Raghav.
Yes,
Okay.
uh, I joined a bit late, and I wanted to ask that for the assignment that we got for the first week,
Yes.
uh, I had some problem solving the questions with the Opamp
Okay.
because it had like the it had like a feedback from for both the terminals.
Yes, yes.
So I wanted to ask whether we'll go through similar
Yeah,
questions
I'll be
today.
talking about that today.
All right.
All right. Anything else?
No, that's it.
Okay.
Uh,
For other
Hello,
people.
sir.
Yeah, Ankit.
Uh,
Hello. Yes.
Good evening. My only doubt is like this is a theoretical course, but as you
Yes.
refer to the PDK and all,
Huh.
so can we somewhere in the problem sessions only simulate and get the results of, I don't know, just a hand-on session or something?
Sure,
Can
you
you
can
provide
do.
that?
I mean, in the problem sessions, okay, I'll try to squeeze in. Okay, I'll try
Okay,
to do some sessions I mean, with the simulations. Okay, I will try to do that once.
uh, that will be great. Thank
Okay.
you, sir.
Okay, I'll try to do that. Don't worry about it. Anyway, we'll definitely have one extra session towards the end of the course. I mean, once the 12 weeks are finished, there will be one hour session, 1 hour extra session. Okay, there I will maybe talk about definitely. There I'll definitely talk about the simulation, for simulation things. Okay, but anyway, I will try to your squeeze in the simulation thing in the middle also. I'll try to do that. Okay.
Okay, sir. Thank you.
Yes. Welcome. Anything else? I'm surprised no one has asked me anything about the motivation for the course. So you all know how and why are you doing this course? Do you all know? And what is the purpose of this? Do you all know what and why are you doing this course? What's the purpose? Is the purpose known to you for the course? Well,
No, sir.
I only see one hand. Okay. So see, I'll just briefly tell you for those who do not know. You see, you must have been going through I mean, you must have been hearing a lot of news nowadays, right? Government is doing supporting a lot of chip companies nowadays. It's investing a lot of money in the chip industry, right? Something like that you must have heard, right? So see, the government is spending a lot of money, but that is in the digital part of the chip. Okay, so we are talking here about the analog part of the of designing. Okay, so you see, whenever you talk about whenever you talk about, so if you are just if you are so you are in this domain, right? Let's say you want to tell your parents what are you doing. So what will you say? The moment you say you are in electronics, the only thing that they will understand is computer, right? That something is so can you make computer or not? Something like that they will understand, right? So people for general people the only thing that they understand when you say electronics is computers and nothing else, right? So so that is why even for a lot of people who are doing this course, they may not be knowing what is the purpose of this, all of this, right? Where is this going to be used? What is the purpose of an op amp, and what all things are we learning? So all those things we do not know. So the thing is that all the signal processing, everything ultimately has to be done. We want it to be done by the computer, right? We want maximum things to be done by the computer because we are very lazy, right? And computer is, as it turns out, is very good at following orders. So we want computer to. Okay, so Viyat or whatever Viyat Shah. Yes, the recordings will be available. Okay, this is the first session. Don't worry about it. All the recordings, all the sessions that we'll be conducting will be recorded. And as a matter of speaking, right now also I'm recording this session, and these will be recorded and it will be shared to you. The link will be shared to you. I'll be posting these recordings on my YouTube channel, and you will be getting the links for those channels for the recordings. Okay, fine. So I was saying that everything that we say or we do, to we want the computer to do it. Okay, however, in the real world, in the world that is around us, nothing is digital, right? Because computer only understand digital, one or zero, right? But everything around this world is not one and zero. It's shades of gray, right? We can say it's shades of gray. It is all around. I mean, between zero and one, there is a lot of things, right? So it's continuous, or in other words, it is analog, right? Analog means continuous. Digital is only about zero and one. Analog is a whole range, right? So in the real world, every information is digital. However, the world in the computer is digital. So we want somehow to process that information from the analog world to digital to such a to a language that the computer understands, right? We want to convert the information that is available in the real world, okay, and we want to convert it to something which the computer understands, right? Basically, we want to convert the analog signals into digital signals, and that is where the whole analog designing comes into picture. So we are basically sitting between the real world and the digital world. We are where we are what is called the interface, right? We help interface the analog world with the digital world. That is what is the purpose of this course. I mean, this is the very first course where you will learn about op-amps and all, but the point is always the same. I mean, the point of everything that you will do in the analog world will be to make sure that it is ultimately usable by the computer. We are always, I mean, I should not say always, but yeah, I would say 99% of the cases where will be uh, the cases where you will be converting some kind of analog signal to digital signal. Okay, the ultimate target is that only. In doing that only, there are various domains. Okay, there is a domain which there are various domains in the analog field. Okay, there are wireless communication fields, so where people capture the signal from the antenna and whatever, and then they convert it and convert, filter, and all those things they do, and finally it is given to the computer inside the mobile phone. So that is one thing, right? So there are other things also in basically whenever we do that, whenever we want to transfer files between two computers, or whenever we want to transfer file between mobile and a computer, so using a cable, all those things, those are also what you are you're converting some information into first analog and then back to digital. So the point being that ultimately, as analog engineers, you will be you will be sitting between the analog and the digital world. Okay, so that is the whole point. And so whenever you learn a course, please keep in mind that this is somewhere going to be used to make sure that the information that is available in the real world is somehow going to be processed by the computer. And it is your job to make sure that this interfacing is done properly. So did you understand the point? Understand the point? Okay. Uh, all right. All right. Thank you. So yeah, I talked a lot now. So pardon my voice because I am not. I'm slightly down with cough right now, so my voice may break sometimes. All right. So let me just start with the course. Yeah. So in the week one again, we learned about negative feedback control. So I hope you do not have any doubt about negative feedback control, right? So you understand what is negative feedback control and why do we need it? Why do we need negative feedback control? If you do not say anything, I'll simply skip. I'll assume that you have understood it very well. So you understood negative feedback control, right? What is the purpose of negative feedback control? What is the purpose of control?
To become stable.
Come again?
For stability purpose, we use negative feedback.
What kind of stability?
If we unnecessary temperatures are increasing in the circuit, then we will use negative feedback to control it.
Yes. So basically, yes, rightly pointed out by your friend. So as it turns out, not only temperature, a lot of things are there in the circuit, okay, which can go wrong. So people for century, okay, have this control thing is a very important thing, right? Whenever you want someone else to do your job, okay, you want to control that person, right? Control that entity. So let's say you are a manager in a company, you are not yourself doing a job, but you are telling someone else to do your job. And if you just leave them be, if you just leave them be, let them do whatever they want, that work is never going to be completed, right? Whenever you give some work to someone else, you make sure that that person is listening to you, right? Basically, you have to control that person's behavior. You have to control that whole flow, right? Only then can you guarantee that the work will be done, right? So the same thing is going to happen in the in everywhere, I think, right? So this is the basic principle of control, that that whenever you want to achieve a target, okay, and you are not going to do it yourself, right? It is a circuit, or let's say if we talk about mechanical system, so it will be something else, right? It will be something else which will be doing your job for you, right? And so that is why whenever someone else does your job for you, you have to make sure that that person has control. I mean, you have control over that person's behavior, or that particular entity's behavior is under your control. Okay, so that is why you need some kind of a negative feedback system, some kind of a feedback system, which makes sure that whatever it is that you desire is being tracked, okay, is being followed. Get my point? So I think you guys understand what is the purpose of negative feedback control. Okay. Now, did you guys understand what is negative feedback amplifier and the whole idea behind it? Did you guys understand what is the purpose of negative feedback amplifier? Okay, so let me ask you then. You guys learned that if you want to make a negative feedback amplifier, we have to do this, right? So, so we say that this is some VI, okay? Okay, yeah, right. This is some VI, and this is some this is some integrator, right? And here you have VO, and here let's say you have a 1 over K factor, right? This is what you learned. So so that in the steady state, this basically becomes VO is equal to what? KVI, right? Right? Yes, good. So you guys can unmute yourself and say something, right? Otherwise, I mean, it is very difficult for me to keep watching the comments. All right. So yeah. So this is what you learned, right? But let me ask you something. This omega u dt, this is an integrator, right? So so integrator, what is the transfer function of an integrator? You guys saw this, right? This is omega u over s, right? The transfer
Yes.
function of an
Yes,
integrator,
sir.
it is
Yes,
omega
sir.
u over s.
Yes.
Yes, good. So omega u over s is the transfer function of this particular integrator, right? Good. Now, what is the gain at DC? I mean, this is a transfer function. So what is meant by transfer function? This is a particular system. Let's say it has a transfer function h of s. If your system is, let's say, Vi, or let's say if it is x of s, sorry, x of s, this is y of s. So what will be y of s in terms of x of s, right? So yeah, and if you say if you want to replace, if you replace s with j2 pi f, so what will it be? So y of j2 pi f will be equal to h of j2 pi f. So this is basically Fourier transform. Okay, so I hope you know this. Yes, it is a steady state gain seen by input frequency, different frequency. Yes, it is right. So x of j 2 pi f, right? So so what is this? So if you take the magnitude, what is this? This is h of j 2 pi f into x of j 2 pi f, right? Right. So if I give if x is what? X of j 2 pi f is what? If it is e to the power j 2 pi f, or rather, sorry, this is not right. So what I'm trying to say is, if you're so in this case, what is x? What is omega? What is h of s? It is omega u over s, right? So this will become what? Omega u over j 2 pi f mod of this, right? Which will be what? Which will be what? It will be omega u divided by 2 pi f, right? Into x of j 2 pi f. So tell me something. At f is equal to 0, what will be the gain?
Infinite.
Infinite, right? So in general, we know that in an integrator, the gain at DC will be what? Infinite, right? And what does it mean, by the way? So this is slightly, I'm digressing slightly, but this is very important that you understand. These are all intuitive. So an integrator, what is the purpose of an integrator? What will it do? Whatever signal you pass through it, right? Whatever signal you pass through it, it will keep on adding it with respect to time, right? That is what is an integrator, right?
Yes.
Yeah, let me just so if this is the signal, what is the if this is, sorry, not this, let's take this for example, uh a simple unit signal, a simple unit step, right? 0. So let's say you pass it through an integrator like this, what will happen at the output? What will you see? Till 0 nothing, right? But after this there will be a ramp, correct? So what is it doing, by the way? At every time it is simply accumulating, right? It is simply accumulating, it keeps on adding to the previous value, right? And that is why, that is how it is going up, isn't it? It keeps adding 1 1 1 1 everywhere, right? Understanding what I'm saying? Right? So the integrator, or purpose of an integrator, is simply basically to keep accumulating whatever is the previous, whatever is the past, it will keep accumulating upon that, right? It will keep accumulating the past for you. So it's a huge bag, it carries a huge past baggage, right? If I want to be cinematic, I would say that if it carries a huge past baggage, it keeps on accumulating everything that is there in the past and keeps accumulating, building upon that, right? So if you see, and someone earlier pointed out that transfer function is what? Transfer function is the steady state value, right? Something like that, something like that someone said, right? A transfer function is what? Transfer function is the steady state gain seen by the input signal at different frequencies, something like that someone said, right? Correct. So when I say it's a unit step, what is the frequency of this? Frequency is 0, right? Someone said 0. Well, not precisely 0, because you see unit step has a something of this kind behavior, right? So it has a lot of frequencies, but if you only talk about, let's say the unit step was I mean, you're not worried about what was happening here, okay, but you are looking at it at very, after very long time, so then it will look like it is only DC, right? So only DC has frequency 0. And what is DC? DC is a simple straight line. It does not have a, it never started from anywhere. It never finished anywhere, right? One second. So who is our niche? Anyway, yeah. So uh, a DC, a DC is something of this kind. Okay, a DC is something of this kind, and a unit step is what? Unit step is something which does this. So the difference between unit step and a DC signal is that a unit step has had a start somewhere. Okay, DC does not have a start anywhere. It keeps it. No one knows where it started. No one will know where it will end. Okay, it will. But for a unit step, there is a start. There is a start somewhere which we know precisely, and that is the only difference. But if someone is looking at a very far end in this direction, if someone is looking at a very far end in this direction, the direction that I've shown using the arrow, then that person will not be able to differentiate between a unit step and a DC, right? Is that point understood?
Yes.
Good. So basically a DC signal and a unit step signal will be looking kind of the same if someone is looking at a I mean, after a very long time, right? Or in other words, if someone is looking at a steady state, then DC and unit step will look roughly the same, right? Good. So tell me something. What does it look like if you pass a unit step through a integrator? What were you saying? It will keep on ramping, right? It will keep on ramping. So will it ever stop the ramping? Again, as I said, please unmute yourself and say something. Very difficult for me to keep tracking the comment section. All right. So it is practically, I mean, it is not possible. It will never stop, right? The ramping will keep on growing, right? The ramp will keep on growing, right? As long as there is something at the input, as long as there is this particular signal at the input, the output will keep on responding. The integrator will keep on adding it, right? And output will keep on increasing. So at the steady state, what can you say at the output? What will be the output at a steady state? Due to this particular input which is unit step.
Infinite.
Yes,
Infinite.
exactly. So I hope everyone understood that. That basically when you have a unit step, okay, that you have applied at the input, due to that the output will keep on growing. Okay, it will keep on growing, and in the steady state, or so that is not right to say steady state, but for time being let's assume this, okay, that in the steady state, what can you say? It will keep on growing and it will grow up to infinity, right? It will not stop even then. So a steady state is what is meant by steady state? Can someone please tell me? And this is all the basic things, right, which you have already seen in the past courses. I'm just recapping it. So what is meant by steady state?
When the output stabilizes to a single value.
Well, not necessarily. There is always a periodic steady state also, right? One second, please. I'm not able to hear you. One second.
When the system reaches almost 99% of the final value, desired value.
No. Okay, so I understand. So that is not correct to say. Okay, you see, there is always a steady state. What you are saying about it, what you are talking about is the uh, again, that is not a steady state. Okay, 99% all those things, that is not steady state. Cannot say that. So what? So
Uh,
steady state, yeah.
when
Say, go on.
yeah, when the output is within some finite bounds.
Okay. So I know that you are able to feel it. Okay, I think you are able to feel it. You are just not able to put words to it, right? You see, steady state means that system has become steady. Okay, it has become steady. Steady means what? That for all practical purposes, no, not all practical purposes, that is not a right word to say. Steady means that whatever change is happening is steady. Whether change is happening or not, okay, so there are two cases. There can be changes in the steady state also. In a small time, there can be changes, but that will keep repeating or that will be steady. Okay. Uh, there will also be a case where there will be no change. It will remain fixed. So the point, I mean, one of you had said that it will remain fixed to a single point. That is true. That is also a steady state, but that is only one particular type of steady state. There can also be a steady state which can be achieved in response to a periodic disturbance in the system. Let's say, for example, we always talk about sinusoidal steady state, right? Sure, right? You have always talked about sinusoidal steady state, right? So let's say this is V sine, sorry, V input is equal to, let's say, A times sine omega t. Okay, if this is the signal, but this is not a signal. I mean, this signal I am not giving. I am giving a slightly different signal. Let's say I am giving a signal A sine omega t times u of t. So how will it look like? How will it look like? Tell me quickly.
Sinusoidal wave.
It will be sinusoid, but okay, let's do this.
Uh, would it be like adding as well and going to infinity?
No, 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 no. It is u of t. U of what is u of t? What is u
Unit
of t?
step. Unit
Yes,
step.
unit
Step
step, right?
function.
Sinusoidal chart will have a DC value of 1.
One second, one second. I am multiplying it, right?
Only positive part of sine wave.
Yes, exactly, right? So you see, I am multiplying unit step with this. So unit step has this kind of a behavior, right? It will remain 0 for t less than 0, right? So this is your unit step, okay? And sinusoid is being multiplied with that. So it's a sinusoid like this. So, sorry. So if you multiply, or rather, let me use a different color here. This is not a good one. Okay. Okay. So when you multiply these two, what is going to happen?
We'll have sine omega t for t greater than 0.
Yes. So this is gone, right? This will be gone, right?
Yes.
Yes. So this is the kind of signal that you have applied on this particular in this circuit, right? It's an RC circuit. Okay, Shubham, I will come to that point in a few minutes, but let's first discuss this. Okay, this is also important because this is the basics. Should be able to understand this first. Okay. Yeah. So I have applied something of this kind, a signal of this kind. I applied a signal of this kind to this particular circuit. So tell me now what is going to happen? How will the circuit behave? Okay, first tell me what is going to happen after a very, very, very long time. After very long time, what is going to happen?
Cap will charged, fully charged.
Cap will be fully charged. Okay. Now, mind you that
Charge,
this that the
charging.
signal is not this. Signal is not this. Signal is this. Okay. Please mind it.
It
It
will
is a
be charging
sinusoidal
and
signal.
discharging both.
Huh?
Charging and discharging both. I mean,
Yes, right?
it will remain a sinusoidal at the output.
Exactly. So basically, we know that for a RC circuit, we know what is the response? It will be 1 over What is this? Tell me. Is that right?
Yes, sir.
Is that right? Is this right? I mean, this is already seen by you in this
Yes,
week,
sir.
right? It's a first order system. So I'm talking about this at a very after a very large, very long time. Okay. So this is the response that that you expect after a very long time, right? And what do I mean when I say very long time? It means that the circuit is in its steady state. Got it?
Yes.
The system is in its steady state, and after and in the steady state, we know that the response of a RC circuit is something of this kind, right? If you excite it with a frequency omega, then this is what you're going to see, that there will be a phase shift and there will be a magnitude, right? Okay, all right. So, but tell me what is going to happen immediately after this point? After this point, tell me what is going to happen. So this is right at the beginning of the application of sinusoid. What is going to happen? Before this, before this, there was no signal, right? It was zero, right?
Yes, sir.
Yes.
Yes, and immediately after this, what is going to happen? After t is equal to zero, what is going to happen at this point? What is going to happen?
Capacitor will
Uh,
charge.
Cap will
Start charging.
cap will start charging, right? And what will be the differential equation?
1 by c integral I C dt.
Correct. 1 by c integral IC dt. 1 by c integral IC dt. And what is IC? So this will
Current
be what?
flow.
V0, right? V out. So dVO by dt is equal to what? 1 by c IC, right? Correct. And IC is what? IC is Vi minus V0 by R, right? So this is the differential equation, the famous differential equation that we know. So with this particular differential equation, the capacitor will start charging here, right? Correct.
yes.
Correct. Sorry. It will start charging here. So let me just put it in this manner. So it will start charging something of with this kind of a behavior, right? It will start charging like this, something of this kind, right? And it will do something we do not know about it, but initially it will not have this particular equation. It will not follow this particular behavior, right? The behavior that we saw in the steady state, isn't it? This is no, right?
Yes.
This definitely is not the behavior that is going to follow in the steady state. Here it will be some kind of a curve it will follow, but it will definitely not be. So it will keep on growing, right? It will keep on growing, and only after this it will start decreasing. So it will definitely not be something of this kind. It will follow some curve. So what I'm trying to impress upon you is that at the start of the at the very start, when the system was excited with this particular kind of a signal, the system was not in the steady state. This is kind of a transient state for this particular system, right? This is a transient where the system has yet to achieve the steady state. It is moving in that direction. Okay, let's for example, or for analogy, you can understand it in this manner. Let's say you are in a train. Okay, you say that the steady state speed of the train is 100 kilometer per hour, right? You say that is the speed, but definitely the train will make a stop somewhere, right? Right. The train will make a stop at a certain train station, and when it stops and when it starts after that, it will start slowly, right? It will start gradually. It will start gradually and it will take some time for it to achieve that steady state speed, right? Correct? So that is the kind of analogy you can understand, you can draw here. It is that this system also is kind of like that only. When you start it, when you apply a signal to it, it will take some time for it to respond to that, okay, to achieve the steady state. But and that time where it is still not in its steady state, it is called the transient period, okay. And once it achieves that steady state, it will follow this particular behavior. Got it? Okay. So the reason for me to explain all of this was to help you understand steady state. So the steady state is basically, yeah, here also, yeah, the point that I completely forgot here. Okay. I was saying that a steady state also has some time variation, right? So here also, you have excited your signal with a sinusoidal signal. You have excited your system with a sinusoidal signal, and you can see that in the steady state, the output is not constant, right? It is oscillating, isn't it? Isn't it?
Yes.
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 So in the steady state, definitely has two kind of behavior. There are two types of steady state, if you can say, if you can think of it in that manner. That one will be a steady state where, as you rightly pointed out, everything will be constant. Nothing is changing. Okay. However, there is also a different second type of steady state where it will be changing, but that change will be steady. Okay, it will be steady, it will always come to the same point, or basically it's a periodic steady state. Other way to say it is, the other kind of steady state is a periodic steady state, where it will always come to the same point after a certain time period. Got it? The change is periodic with a time period, with a fixed time period. That is also a steady state, perfectly fine steady state. Okay, these are the two kind of steady state which you will encounter in your journey. Yes, so Chirag, this is the right again good question. Yes, in a RC circuit, actually after not after a very long time, ideally after infinite time, you will see a this thing. If you have a sinusoidal of this particular kind, if you have an input excitation of this particular kind, where you have also a multiplication of ut, okay, then only after infinite time will you be able to see the steady state response, because the initial transient will die down with a exponential of minus t by rc. Okay, so if you do the maths, you will be able to see this. Yes, Ravi, you have a doubt?
No, I just want to ask whether this A sine omega t into ut, that's a practical signal, right? I mean,
Yes, that's
in
a practical signal.
practical, this A sine omega t is not a practical signal.
No, no, a sine omega t is not, a sine omega t is not a practical signal by me. I mean, you can generate a
I
signal
mean,
like that, but again, as any signal that you will be generating will have certain start time, right? It will start somewhere.
yes, yeah. So that is why, if ut is there, so those will be practical signals,
Yes,
right?
it is a practical situation. Yes.
Okay.
So
Yeah.
when I
Thank you.
said only after infinite time you will be able to see the steady state response, this is this is mathematically precise. Okay. However, for all practical purposes, after 5 or 6 time constants, okay, after time which equals 5 or 6 time constants, you should be able to see steady state. It will not change much. Okay. All right. So, Jayan, Girdhar, yeah. So it's an exercise for you. Please try out how the equation of this steady state came. Please try it. It's a very basic thing. It is covered a lot in the basic circuit theory courses, so you should be able to do it. Anyway, so this is something which yeah. Now let me come back to the point here. So in this case, uh, let me come to this particular case. Here you are giving a unit step, right? And it keeps on integrating and it keeps on ramping up. So what do you say? What will happen to the steady state behavior here? First of all, let me ask you, will you ever get a steady state, a mathematically precise steady state here? No, right? I mean, here you will never get a steady state. Okay. So that is why, so whenever you do not get something practical, you say that it is, I mean, the mathematicians came up with certain numbers, right? Infinity, tending to zero, tending to infinity, some kind of numbers. Mathematicians came with those numbers, right? Whenever they were not able to find out exactly what is going to happen, something like that. Okay, so here also, since you will see that in this case, you will never be able to achieve steady state, it will keep on growing, right? So in some world where, let's say, there is an end of time, okay, so in some world where there is an end of time, what will be the value here? It will become too large, right? Till the end of time, right? It will keep on ramping till the end of time. It will become very large. Large as in infinity, right? So that is why when you say you are integrating a unit step, the steady state value of that will be infinity, right? The output of that will be infinity, isn't it? And as one of our friends told earlier, that the transfer function is what? It's the steady state gain at a certain frequency, right? So here, what was the input frequency for unit step? What was the input frequency?
Oh,
Come on, guys.
there are there are infinite
Yeah,
frequencies
that
in
is
this.
true. But again, as I said, if someone looks at it after a very long time, they will not be able to distinguish between a unit step and a DC signal, right?
Yes.
That is very right point, whatever you said. But what I'm asking is, I mean, here also, after a very long time, what is the frequency that you will be seeing here?
Oh, that would be a DC essentially.
DC, right? It is zero.
Yes.
Frequency is zero, right?
Yes.
Correct. And what was the response of that at the output? What did you see? What is the output?
Oh, it was ramping up infinitely.
Yeah. So the value at DC for a signal given at DC, the output of the integrator tended to infinity, right? It kept on increasing
Yes.
till infinity. So what can you say about the gain of this particular integrator at DC?
That's infinite in that case.
Yes, it is exactly infinite in this. No, no, it is exactly infinite. And what did you see here?
Yes, it
Infinite.
would have to say that
Right?
infinite.
So yeah, so exactly it makes sense. What I'm trying to say is that everything, whatever maths comes out, it makes sense somewhere, right? It can be actually measured. Understood? Here, all these things that you see through maths can actually be measured. It's a very practical thing. Got it? So I hope that you will never forget this now. What is the DC gain of an integrator? Okay, I hope you never forget this. That an integrator has infinite DC gain. Got it? Yes, Ravi. You have a question?
Yes. So like here we said, I mean, when we see at infinity, it's kind of a DC, and then we are seeing an infinite gain.
Yes.
I mean, so I was just talking about the like the frequencies. So I'm just thinking in those terms. If there are infinite frequencies, I mean, how can we look from the frequency perspective, like response to those frequencies?
You see, in this case, there are infinite frequency, but those infinite frequency responses are going to die down. You see, how can I say? So this is the situation, right? The moment
Yes.
it jumps here, yes, it will have a lot of frequency components will be there, right? There will be a lot of frequency components, but all of these frequency components will gradually die down after infinite. As in this case, there will also be a lot
Uh,
of sorry, let's use this color. Here also there will be a lot of initially there will be a lot of frequency components, okay, because this is a transient, okay, Ravi.
right. Yeah. Yes.
But
Yes.
these
Got it.
transients are going to die down after a very long time. because they are going to die down with exponential minus t by rc. Got it?
Yes. Got it. Okay. Thank you.
So they will die
So
down after a very long time, and at the steady state, the response that you will be left out with will be only because of the excitation that you are giving. Okay. Similarly, in here also, the frequency initial frequencies that will be generated here, there will be a lot of frequency here, but the response of them will die down eventually as the ramp is rising. Their response will die down. Got it?
yes, got it. Thank you.
And after infinite time, after very long time, the response that you will be getting will only be because of the DC. Okay?
Yes. Thank you.
Yeah, welcome. Yes. So now that you are clear, now let me come back here and ask you this question. So, so what we are doing here is uh, we are basically comparing our input, right, or rather output, and first we are since we are trying to get a gain of k, we are attenuating it by k and then feeding it back here, right? That's why we call it negative feedback, and we are taking the no, that is why we call it feedback first. Okay, that we are taking the output here, we are sensing output here, then we are attenuating it by k, then we are feeding it back here at towards the input. And since we are taking a subtraction at this point, that's why it's called a negative feedback, right? And we are what is that we are doing next? The error that is being generated here is used is being fed to an integrator. Okay, it is being fed to an integrator which integrates the error to get somehow the output voltage, right? But as we saw, the integrator itself has what? DC, infinite DC gain, right? It is infinite DC gain. Got it? Good. So we were trying to make an amplifier, right, of gain k. Let's say we were trying to achieve this. VO is equal to k times Vi. We are trying to achieve this. But in achieving this, we need something which has infinite DC gain. So don't you think it's kind of really absurd? I mean, if we have this infinite DC gain, why do we need to make a gain of k? And we can always, if we are able to generate an infinite DC gain, we can as well have gotten a gain of k, right? Are you able to understand my question? My doubt?
Yeah, but in this case, V is also varying, right? And when it is becoming DC, so at that value, it's like almost zero, very small.
No, no, I
Even
understand
infinite gain.
that. Correct. What you're saying is correct, but that is the operation of this particular thing. I'm saying that why even need this thing? We can always do this, right? If we are having a gain of infinite gain, if we can somehow make infinite gain, let's say infinite is nothing, never possible in practice, right? Infinite is never possible in practice, but let's say engineers are so advanced that they are able to somehow get very large gain. Let's say gain of 10 to the power 5 or 10 to the power 8, something like this, that engineers have somehow devised somehow made some circuit which can get a gain of 10 to the power 8, and they went ahead and did this particular thing, right? But why do this if you are able to get a gain of 10 to the power 8? And I'm pretty sure, I mean, you should be pretty sure that getting gain of 10 to the power 8 should be much more difficult than getting a gain of, let's say, 5, right? Then why did engineers do this thing? To get a gain of 5, why did they have to get a gain of 10 to the power 8 first and do this particular thing? So now are you able
I
to
mean,
understand my question?
is that gain stable? So 10 to the power 8.
Good. Exactly. So that is the moot point here. That you see, again, coming, this is the whole crux of the matter. The whole crux of negative feedback requirement here is that you will never get a gain which will be precisely 10 to the power 8. Okay, you will never get a gain which is precisely going to be 5. No one can make that. I mean, to make that only we do all these things. One cannot guarantee a gain which is very high, which is precisely something. But however, in this case, we require a gain which is precisely 5. Okay, one needs the engineers want to make a device which can guarantee a gain of exactly 5 or whatever k you want here. And for doing that, what they did is they say that okay, so we do not have something which can in one step guarantee a gain of 5, but we have something which has a very 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 large gain. This gain can be 10,000, 10 lakh, 10 crore, don't know. It will be very high. It can vary, but it will be very high. That much I can guarantee. That is what the engineer said, that I can guarantee a gain which will be very high. However, it can vary. It can vary between let's say 10,000 to 10 lakh, but still it will be very high. So after that, they said, okay, if you can give me certain, if you can give me that device which can have a very 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 large gain and it can vary, using that I can make a system which will be very good in terms of which can provide me a very good gain, very good smaller gain. Getting my point? So basically, that's how the whole concept of control comes here. That one second. Hello? Yeah, I think I'm audible. Okay. So that's how the whole concept of negative feedback comes about. Is that give me a device. The idea is to give me a device which has a very large gain, and using that I can make a system which can guarantee a very precise gain of V naught is equal to KVI, right? And in this argument only, the whole concept of negative feedback is kind of hidden, right? You also learnt about this thing, right? Unity loop gain or loop gain bandwidth, something like that. You learnt about this, right? Loop gain bandwidth, unity loop gain frequency, right? Yes. So what is the point of loop gain? What did you understand by loop gain or loop gain unity bandwidth? What is that?
Loop gain can be helpful to determine the stability check for a system.
Okay, don't go there. Okay, first let's keep stability will come later. Okay, let's first stay here and try to understand what is the significance of loop gain first. So using the whole argument that I just made right now, that you need a very large gain here, right? You need a very large gain here, and using then you can guarantee that the system very precisely can track V naught is equal to KVI. So from that, can
So
you? Yes,
we can have an output on which we have control.
yes, you can have a control, right? So what is the significance of where does loop gain come into picture here? Why do we talk about loop gain?
To understand what part of the output is fed back, how much uh, part of it is taken.
Something like that. I mean, yeah. So basically, again, as I said, engineers couldn't make a device in one step which had a very precise gain. Okay, they could not do that. However, they said that once you give me a device which can have a very large gain, variable gain, however, but very large gain, I can use that to make a device, to make a system which can give me a very precise gain. So the whole reason for having a loop gain concept is hidden in that argument only, right? That you first need something which can have a very large gain, right? You first need something which has a very large gain in the system. Only then can you guarantee this, right? Only then can you guarantee this. So the loop gain here is what it is basically saying, that what is the gain once you what is the, as our friend rightly pointed out, what is the gain when you traverse the loop? How much is the signal amplified when you traverse the loop? And what is the significance of that? What is the meaning of that? What is the usefulness of that? It is basically saying that, let's say you have some error here. Okay, let's say you have some error here. How much of that error comes back to the input? That is the point. As long as a large amount of error, I mean that error keeps getting, as long as the error here in the as long as the error keeps getting amplified in the circulation here, your system will behave properly. That is the whole point of loop gain. Okay, as long as your error here is getting amplified and then circulated back, you are good. There is no problem in the feedback loop. Your feedback loop will keep on working. The problem starts only when your error here is getting suppressed by itself. The error is not suppressed by the loop action. It is suppressed because the loop itself does not have any gain left. So let's say your error here was, let's say you want to achieve 5 volts, or rather let's say you want to have 1 volt here, k is equal to, let's say, 5. So what do you expect here in steady state? 5 volts, right? If
Yes.
you Yeah, if your k is 5, you expect 5 here, right? Or rather 1 over k is what? 1 over k is 1 over 5. So you expect 5 here at the output. Now that will happen as long as your V error, whatever it is getting here is getting this thing is getting integrated, and it keeps on happening, and steady state will happen. However, let's say you made a system here which, instead of amplifying, was reducing the error. I mean, let's say it was 1 over 10. It was a simple attenuator which was simply attenuating the error 1 over 10. Can you ever achieve this? V naught is equal to 5 volt using this in the steady state?
No.
You'll not be able to, because in this case, what is happening? The error, please be mindful that the error is the thing which is the most critical in this particular loop operation. The error has the information of where you need to move. Okay, the error itself, the error quantity has the information of in which direction the loop has to act and how much it needs to act. Got it? The error has that information of how much the loop needs to act and in which direction the loop needs to act. So if the error signal itself is getting attenuated somewhere, then you are what? You are gone, right? You are screwed, isn't it? The loop will not work because you are attenuating the very information that is needed to make sure that the loop works. So that is why the loop that is where the loop gain comes into picture. Loop gain simply means that the error here is it keeps on getting amplified as long as it is in the loop. It is in the it as long as the loop, when you circulate in the loop, the error amplifies, something like that. Okay. So you think about it once, when you after this session you will be able to understand it. If you do not, I will probably try to give you a different kind of a picture next time. So today I think this has to end. Yeah. Last thing that I want to talk about is this. This is a very important thing. I also will talk about a little bit about Opamp. I think Opamp everyone knows, right? How Opamp works overall. I mean, okay. Sandeep, you are right. The error finally reduces to zero. I'm not talking about that. I'm talking about the error in the loop. How do I say? If you traverse across the loop, if you go in the circle across this loop, this error will actually, you see that error will not become zero. It will become amplified. Okay, I will. Okay, so hold on to that. I will talk about it in the next class. Okay, how this actually works. Today I do not have the time, so maybe I should not have given that kind of an analogy. It creates confusion. So today just try to understand that the feedback in itself will work only when the loop gain is very large. Okay, and what is loop gain? It is the gain which you will see, which a signal sees when it moves in this kind of a fashion across the loop. Okay, that is the loop gain. I'll talk about it in a different manner in the next class. Probably that will clear the confusions. Okay. Yeah, so I was saying about op-amp. So op-amp, I think everyone knows, right? What is op-amp? More or less. Okay, good. So a little bit of, If you know that, maybe just a little bit revision can help. Okay, this is op amp. So in an op amp, what happens is you have three terminals. Okay, this is let's call it plus. This is minus. This is VP. This is VN, and this is VO. Okay, this is an op amp. So the inside of an op amp, it will be a very complicated thing. It will be implemented using transistors, but the block level diagram, if you want to represent it in some kind of a resistors and control sources equivalent, it will look something of this kind. Hmm. Okay, so this is how it looks. Okay, on top of that, it also has supply voltages. Okay, so this is an op amp. Okay, and what can you say about for an ideal op amp? What can you say about RB? What can you say about
Infinite.
RB?
That should
What?
be infinite.
Yes, it should be infinite. Good. And what can you say about A?
It's infinite.
A
Good.
infinite.
Okay. What can you say about R0?
0.
Zero.
Good. What can you say about VDD and VSS? Sorry. First tell me what can you say about VDD? This is also infinity. Okay. And what can you say about VSS?
Minus infinite.
Yes, it is minus infinity. Okay. Good. Moreover, also you have to understand that for this op amp, the gain does not depend upon frequency. Okay. 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 For an ideal op amp, the gain does not depend upon frequency. Please remember that. All right. However, for a real op amp, there will be all those things. All those things, all the things that I mentioned here, none of them will be true. I mean, none of them, or I mean, one or all of them might not be true for a real op amp. Okay. All right. So now that we have this, so this is the picture of an op amp. So for an ideal op amp, the picture reduces to You have Vp, Vn, this is plus, this is minus, and this is what it is. This is Vo, and the picture is Vo is equal to A times V plus or Vp minus Vn. Okay, this is for ideal op amp, or rather, this is A, right? So A has to be infinity. Okay, this is for ideal op amp. Okay. In a lot of cases, you will be seeing that you can ignore RB and R0. Okay, in which case the picture is actually exactly the same as this. It's just that A will not be infinity. Okay, okay, yeah, fine. Now that we have understood this, let's quickly discuss a little about passive sign convention. That is a very important thing. After that, we'll discuss one or two questions. Okay, so anyone knows what is passive sign convention?
It is power delivered or power cons
No, no. What is that?
the current direction
The
basically.
current in which the terminal in which the current enters is taken as positive.
Okay, good. So, so let's say you have a terminal. Sorry, let's say if you have any element here. This can be any element. Okay, resistor, capacitor, doesn't matter. Any kind of resistor, capacitor, inductor, transformer, your mutual inductor, or a voltage source, current source, doesn't matter. Any element. Let's say you have. And right now I'm talking only about two terminal element. Okay, I mean any element can I mean elements can have a lot of terminals, but at a time I will only be concerned about the two terminals that I'm dealing with. Okay, that is why I told that I can also talk about mutual inductors and transistors and anything. They can have more than two terminals, but at a time I will only be concerned about the two terminals that I want to look at. Okay, so let's say these are the two terminals. What I will do is I'll define this thing, a plus and minus sign to it. I'll simply, in my own way, I'll simply assign a plus and minus sign to the two terminals. Got it? So let's say this is terminal number 1, this is terminal 2. I say that terminal number 1 is positive. Sorry. Yeah, hello? Yeah. So I'll say that terminal number 1 is assigned positive sign, and terminal number 2 has been assigned a negative sign. Okay. Once I do that, now according to passive sign convention, please listen to the statement very carefully. Once I assign a positive and a negative sign to the terminals of my element, according to passive sign convention, a current which is entering positive terminal will be termed as positive current. Okay, a current which will be entering the positive terminal will be taken as positive current. A current which will be exiting the positive terminal will be taken as negative current. Got it? Is that point understood? Okay. If that point is understood, I'll anyway write it. Uh, Okay. Needless to say, the current exiting the positive terminal and entering the negative terminal is taken as negative. Got it? So this is the passive sign convention. Now, once you have the signs in place, once you have all the signs of the currents and voltages, what you can do is, after that, the power is what? Whenever you say power, it is always power dissipated. Okay? The power dissipated is simply V into I. Okay? With the signs, definitely with the signs here. You have to multiply V and I, and they have to be with their proper signs. Okay? So tell me something. If so let's now ask the question. So you have an element, for example, you have an element here. So this is important. So let's do this. Okay. Now, for example, let's say you have an element here in which this is the situation that it is 2 volt, and the current is in this direction, which is the current flow is in this direction. It is 2 amperes. So tell me, what is the power dissipated here?
Plus 4
4 watts, right?
volts. Watts, sorry, yeah.
Yes, exactly. Tell me another thing. So this is example number 1. So for another example, let me ask this question. Again, this is 2 volts. However, the current is in this direction. So what is the power dissipated?
It will be minus 4 watts.
Yes, it will be minus 4 watts. So whenever the power dissipated is negative, it means what?
Absorbed.
No,
Sorry,
no.
delivered.
Yes,
Deliver.
it is delivered, right? It is not dissipating power, but it is delivering power, right? That is what it means when we say the power is negative. Okay, good. So now let me ask you a third question. It is my question is, what is the power delivered here?
-4.
Exactly, right? Minus 4 watt. This is the power being delivered by the element. Okay. When I ask the power delivered by the element, it is minus 4 watt. When power delivered is negative, it means what? The element is?
Dissipating.
Yes,
Dissipating.
it is dissipating power. Exactly. Good. Good. Now that we are clear on all of these, now let's solve quickly one question. I think I'll not solve, sorry, I'll not solve this question because this question is part of your assignment. I cannot solve it. This is mandated in our session. So this is not for me to solve. I'll, however, tell you what to do. So before doing that, let me uh, let me clear this doubt first. I think I think this is the right class to discuss this particular point. I should not have left it in confusion, loop gain and all those things, because this is very important. See, earlier when I said when I talked about loop gain, I said something and also please forget that. Let me again rephrase whatever I'm trying to say. See, how does loop work? By the way, how does loop work? How does the loop work?
Takes a portion of the output to the input side and
Yes,
does
it
a
takes a
comparison with the
portion.
actual input,
Yes, good.
and
And
based on the
compares it.
error generated, it drives
Huh?
the output in the appropriate direction so that the
Yes,
error is minimized.
yes, exactly, right? So what happens is the output is not directly compared, part of it the output is compared, right? based upon what is it that you desired. I mean, how much of the input you want to be amplified. Based on that, sorry, based on that, you basically take a part of the output and you compare it with the input, right? And then while comparing, you subtract it, right? I'm definitely comparison and subtraction only, but yeah. So you compare the output, a part of the output with the input, and then the error voltage, the error that is being generated here, that is fed to a controller, right? That error is fed to a controller. Please mind it. This guy here is a controller. Okay, the error that is being generated by the comparison, okay, that is being fed to a controller, and that controller then what does it do? The controller takes the appropriate action. Okay, it then decides what to do with the output, whether to take it up, whether to take it down, and how fastly, how quickly it has to take it up or take it down. Are you able to understand what I'm saying? That is the purpose of a controller. So this guy here, this is a controller. And what kind of a controller is this? If you have done control theory, you may have heard three types of controllers: proportional controller, integrator controller, differential controller, and then again there is one which is PID, which is proportional integrator, proportional integrator and differentiator kind of a controller, all combined
Yes, sir.
together, right?
It's PI controller.
Come again?
It's the integral controller.
Yeah. So it's an integral controller, correct? And what does an integral controller do? It keeps on taking the error and keeps on accumulating it, which means what? It keeps on it takes the error, okay, and then it integrates the error, and based on that it drives the output. The best thing about an integral controller is that it will never stop integrating. It will never stop unless the error is zero. Okay, I'm talking about DC picture here. That if let's say if there was any error left here, it will keep on integrating it. It will keep on integrating it till the output becomes infinity, right? Isn't it? In the
Yes.
steady state, let me ask. Let's understand it. We already saw that the steady state gain of an integrator is what? The steady state DC gain of an integrator is what? It is
Infinite.
infinite, right? So let's say I'm saying it is, let's say in the steady state this V is not equal to zero. Okay, I'm talking about DC right now. Okay, let's say this V is not equal to zero. What will happen to the output, by the way, in that situation?
It will be infinite.
It will keep on growing, right? It will go up to infinity, huh? Isn't it? And that is something which is not possible, because the moment it rises, the moment it start rising, it is already it is already being fed back at the input. It then that again it is being compared to the input, right? Such that the error has to go down to zero, right? The error has to go down to zero, because the direction of the feedback is such that it has to enforce that the error has to go down to zero. Let's say if the error is not zero, but let's say the error is equal to 1 volt. Okay, what will happen? It will keep on rising, right? The VO will keep on growing up, correct? It will keep on growing up with time. However, please note that this is also being compared to the input at the same time. The moment V out, it rises up, what will happen? The difference will reduce, right?
Yes.
Yes.
I mean, are you able to visualize it, or I should write it exactly? So you see that if V is 1 volt, which means what? It is 0, right? Right now, for the values that I have given, if V is 1 volt, which means what? This is 0, right? V out is 0, right?
Yes.
Yes,
Okay.
sir.
So now tell me, if V is 1 volt, V out is 0 here, which means 0, it is also 0 here, right? Because 0 by 5 is to be 0, has to be 0, right? So it is 1 volt. Now what will happen? The integrator will start ramping up, right? Start ramping up the voltage here, right? Okay,
Yes.
it will start ramping up, The moment it increases slightly, even slightly, the moment it increases it even slightly, a part of it, let's say it has increased up to 1 volt. Okay, let's say the V out has increased up to 1 volt. What will happen? 1 upon 5 volt will come here, right? And then the error will become what? What will the error become after that?
4
4
by
by 5.
4/5.
Right? It has reduced, right? It has reduced. And what is forcing it to reduce? It is a sense of feedback. It is not adding. It is negate. It is becoming. It is trying to reduce the error. Got it? The output is being subtracted. The part of the output is being subtracted from the input in such a way that the error has to reduce always. It cannot keep on growing. Right? Right? So what will happen is, so in other words, if you see, if you want to find out if one, if let's say, if you want to find out uh, mm, okay, again, let me rephrase again. So you already understood that the gain of this guy, I mean, that the loop is making sure that the error keeps reducing. But could you able to understand where in the loop is that happening? I mean, why is this actually reducing and not increasing? How could you have understood it very well that this is actually reducing? I mean, just by looking at it, you could say that okay, this will always be a negative feedback. What is the critical
Uh,
element that is making sure of that?
so the
Give
comparator, where we are comparing at the
Okay,
input.
so let me ask you this. Let's say if this was not 1 by k but minus 1 by k, what will happen in this exact same scenario?
it's
Oh,
increased.
it
Positive
will
feedback.
be a positive.
And what do you
Error
why do you
will
say that?
increase.
So it would keep on increasing. The error would also increase, and then
Exactly.
the output would keep on increasing.
Good, very good. So basically what you're doing is you are actually looking at what will happen to the error, right, as it moves in this loop, right? Isn't it? Whether the error sign is flipped or not. That is what you're seeing, right? If the sign of the V error is getting flipped while moving in this, which means that, which means what?
Means
Uh,
error is decreasing.
uh, Decrease in there.
Yes, exactly. But so yeah, so okay, so without, let's say, without this minus, what is happening to the sign of the error, V error, once it reaches back to this point? It is becoming
It's becoming negative.
exactly right because of the negative sign here. Sorry, yeah, because of the negative sign here, the V error is becoming negative, right? Once it moves the whole loop, right? But what happens if you add another negative sign here?
That becomes positive.
That becomes positive, right? So instead of getting subtracted from the input, what will happen? It will simply add, right? The error will keep adding, and that will not lead to anything good. The loop will be destroyed. It will move in the opposite direction. Correct. It is exactly the same as you have a bowl like this. Okay, you have a bowl like this, and you have a bowl like this, and you have a small this thing, a glass ball in here, and you have a small glass ball in here. In one case, in one case, if you perturb it slightly in this direction or in this direction, what will happen? It will come back to its original point, right? So this is a glass bowl and this is a glass ball. This is a container, okay? So, okay. This is a glass container. This is a glass container, and in this you have a small ball like this, glass ball. Okay. Now, if you perturb it slightly in this direction or in this direction, what will happen? Come on, guys.
It will get perturbed a bit and then
Again to
come
the
back to
same
its
point.
position.
Yes, it
I
will
mean, it will
oscillate a
keep on
little bit and
oscillating.
then it will come back to
Yes,
the same point, right? It's classic
yes.
11th class gravitational physics, right? You all have solved this question many times while preparing for many competitive examination. Anyway, so this is classic example of, so this is negative feedback. Okay, what happens is the moment this tries to go up, gravitation acts on it and it says, no, no, don't go up, please come back to me, come back to your neutral position, don't go in that direction. The gravitation acts, and it here in this case, the gravitation acts as a negative feedback force. Gravitation, along with the shape of this ball, shape of this container, acts like a negative feedback for this particular ball. It will never allow it to, not, I will not say never, but it will not allow this ball to escape its neutral position. Okay, this is called negative feedback here. Now let's look at the same thing, but in this case, when the container is flipped like this, what will happen here? If you perturb it slightly in this or in this direction, what will happen?
It will go off. I mean,
It will go
fall
off,
off the
right?
system.
Correct. So here, what is happening is, it is also a feedback system. However, in this case, it is a positive feedback system. Got it? It's a positive feedback system because of the force of gravitation acting on it and the shape of the container that is placed here. The shape of the container is what is it doing here? It is actually facilitating the direction in which it is being pushed. Okay, what is happening in what the difference between negative and positive feedback is that in negative feedback, the system will try to oppose the change that is it will try to oppose the change, oppose the perturbation, okay, such that this system comes back to the original neutral position. Okay, however, in the positive feedback, once the system is perturbed, it will facilitate the direction of that change. It will keep on going in that direction. It will not stop. Got it? And that is all in the circuit case. Sorry, the circuit can be easily understood by seeing by traversing the whole loop. When you traverse the whole loop, and you just have to see what is the sign, what is the sign of the error. Okay, what is the sign of the error voltage that is being generated? For that, the best way to do, 1 second. So Sandeep, the thing is that, yes, in an integrator type of a controller, in negative feedback, you will always have steady state zero, a steady state error zero, provided that the steady state that you are looking at is at DC. Okay, if you are looking at a higher frequency of steady state, that may not be the case. There, the error may not be zero. If at DC you are looking, then yes, it will be zero always in the integrated type controller. Yes. Now to conclude, if you want to see whether the loop is in negative or positive feedback, uh, this is very important, and I'll not take much longer. I'll just finish this and then I'll just discuss the question. Yeah. So So for that, what you need to do, so I'll take again the example of this only. This is plus, this is minus, this, or let's say this is plus, this is minus like this here. This is Vi, this is your controller. Okay. So For to check whether the loop is in positive or negative feedback, first what you have to do is, by the way, did you guys very well to understand that this the sense of V error will not depend upon whether Vi is positive, negative, zero, or whatever. It will not depend upon it, right?
Yes.
So if you simply want to find out what is the sense of V error, we can always do the easiest thing, right? And simply ground it to zero, right? Let's say that V is not even present, Vi is not even present here. If you are only concerned about knowing whether the sign of the loop is what, I mean, whether the loop is positive or negative feedback, if you are only concerned about that, we can as well get rid of Vi, right? Because it doesn't matter whether Vi is zero or any number, right? It doesn't matter because the loop sense of the loop does not change with the Vi. It changes with the sign in the loop, right? It does not matter what Pi is.
Yeah.
Is that point clear to everyone?
Yes.
Yes, good. So, if that is understood, now it is very easy for me to explain this. So, when you want to check whether the loop is positive or negative feedback, first what you have to do is simply make sure that input is not there. So, if it is a voltage source, which is the input, you simply have to ground it. Got it? Okay, good. Now, what you need to do is at the place where the comparison is done, or rather at the place where VE is there, at this place VE, you just apply some voltage. Let's say it's a some positive voltage. Okay, some positive voltage you apply here. Now we all know that when it traverses through the loop, the information, what should happen? It is a positive feedback, sorry, it is a negative feedback. So if the error is positive right now, somehow the loop has to make sure that whatever comes back here at this point has to be positive, right? Sorry, sorry, not that. Please scratch that. So what I'm saying is the error is some positive number here at this point, right? V error is some positive number at this point, V error. Now, somehow, if the loop is negative feedback, what the loop has to ensure is that when this signal comes back here, it should be negative, right? Some negative number, so that the resultant, which is basically this minus this, has to become what?
0.
Zero, right? I mean, you want it to reduce to zero, but it will not immediately reduce to zero. It will slightly reduce, right? It has to reduce eventually. Correct? It has to reduce eventually. So whatever comes back here has to be negative, right? Only then it will add with zero, right? So at this point, the mind it that input is now zero, right? Input is zero. It is 0 volt. So whatever comes back here, it has to add with this 0 volt and then generate the error voltage, right? Right now the error is some positive number. I want to make sure that as the signal passes through this loop, the error after one pass, after one round trip of the loop, their error has to reduce, right? That is the purpose of negative feedback, isn't it? So to make sure that the purpose is fulfilled, I have to ensure that upon passing through this loop, the whatever quantity comes back is negative, right? Only then it will add with 0 minus plus a negative number will result in some quantity which is in the opposite direction of what initially was, right? So ultimately that is the recipe. So what you have to do is you have to first ground the input. Okay, now let's say you apply some positive number, some positive voltage here, some positive V error here. What is going to be the output here, sign of the output here? Is it going to be positive or negative?
Positive.
It is positive only, right? Because omega u over s or omega u dt, it's going to be positive. You apply positive here, the output of integrator will also be positive. Okay, good. Now this positive, when it passes through this 1 over k, what will be the voltage here at this point? It is
It
also
will be
positive, right?
reduced.
Yeah, it will reduce, but it is positive by
Yes.
reduce, but it will be positive, right?
Yeah.
Okay, good. Now this positive, but when it is subtracted from the output, subtracted at this point, what will be the sign of this?
Negative.
It will become negative. So in one round trip, this did change its sign, right? And that was the whole point of negative feedback. We wanted somehow to make sure that whatever was the initial error, it has to go in the opposite direction of that error, right? If it is going high, if it is increasing positive, what should happen? Once it passes through the loop, the information should come in the loop such a way that it should reduce, right? It should go in the negative direction. Got it? So that is how we can confirm here that the loop is indeed negative, right? You just have to make sure that you pass through the loop, okay, and whatever comes back is in the opposite sign of what was applied at the input. That's it. Okay, got it? So now let's apply this to the problem at hand. I'll only solve the first the only give a hint of how to solve this. So in this case, you can see that it is very difficult to judge whether the loop is positive or negative, right? The first question that you should ask yourself when you see op-amp connected in feedback, the first question that you should ask yourself is whether this op-amp is in positive feedback or in negative feedback. That is the first question. Okay. Uh, 1 second. Yeah, the first question that you should ask is whether the op-amp is in positive feedback or negative feedback. So how do you find out whether this op-amp is in positive or negative feedback? Tell me.
We ground the input.
First of all, we do not, I mean, ground the input as in what? Uh, we have to nullify the input, right? You have to nullify the voltage independent sources, right? That's what is meant by grounding here. Why did we ground it, by the way? I simply wanted to make Vi equal to 0, right? I simply wanted to make Vi equal to 0, isn't it? Right? So Vi equal to 0, since it is a voltage source, if it is a voltage source, what is the purpose of a voltage source? It will simply create a voltage V naught across it, right? If I make the voltage source equal to 0, what does it means? It means the 2 points are shorted, right? Right?
Yeah.
Yes,
Yes.
yes.
Yeah,
Similarly,
correct.
so this is what is meant by nullifying the voltage source. If someone says nullify the voltage source, it means what? It means that simply nullify the purpose of the voltage source, simply short it. Okay, the voltage source is not there. Short it. Similarly, if someone says nullify the current source, what will you do? What is the purpose of a current source? It is to make sure that the current is equal to some I naught, right? So how will you nullify it? You make I naught equal to 0. What does that mean? Between these 2 points, no current is flowing, which means what?
One second.
These 2 points are open, right? Yes, these 2 points are open. So when you say nullify a current source, it means open it. And when you say nullify a voltage source, means short it. So what will you do? You will short it, right? First you short it. Good. So I shorted it. Okay, this is not good. I should not be writing here. I should maybe take a copy of this. So please bear with me for another 5 minutes, because this will be done in 5 minutes. Okay. So yeah. So this is gone, right? So this is gone. You shorted it. Now what? Now what should I do? Yes, Ravi. What is the doubt?
Uh, so usually Vi is the input. So how can we determine here this voltage source is input, or do we like nullify all the voltage
No, no.
sources?
You have to nullify all the independent voltage sources and the current sources. Okay.
Okay.
Because they will not disturb the sense of the feedback. Okay, please mind it that nullifying the voltage sources and the nullifying the independent voltage sources and the current sources will not disturb the sense of the feedback, as we already saw, right? Doesn't matter whatever
Uh,
is the voltage. You can always
so
make it zero.
essentially,
Yes.
like, I mean, even if there are more than one voltage source or current source,
Huh.
so they are kind of a input in one way or the other, right? And nullifying them would solve
Yeah, I
our
mean, if you
purpose.
have independent sources, you can just nullify them because independent sources do not change the sense of feedback. Okay, all
Okay.
the independent sources you can nullify. They will not
Right.
change the sense of feedback. I just showed with an example of Vi, but it is true for all the independent sources wherever in the circuit they are connected. Doesn't matter. It will always be the case that because of independent sources, you do not get your sense of feedback is not disturbed. Got it?
Yes. Thank you.
Yes, yes. So now tell me what should I do next?
Sir, calculate the voltage at Vn and the calculate voltage at Vp
Huh,
and the
how? Where is the voltage? How can you generate voltage? Because
voltage.
the only voltage source that was present here, I
Assume
simply nullified it.
assume Vn is equal to V naught and Vp is coming out 3 V naught upon 7. And
Okay.
if we increase little on V naught, then dominating terminal is negative terminal because it is directly V naught. So
Hmm.
we can
Hmm.
negative
Yes.
feedback.
Yes. I understood what you're saying. Okay, good. So, but let's try to understand it in a manner that everyone everyone understands. Try to explain it in a manner that everyone understands. So, as I said earlier, we just have to make sure that the that when that the error voltage you apply something at the terminal where the comparison is done, right? So, as I said here, what do? You give a signal at a place where the comparison is done, right? Here, you give certain signal at the place where the comparison is done, right? Correct? So here, where is the comparison done in this place? Uh, yeah, where is the comparison done here?
At
VN
the input
VP.
terminal of the Opamp.
Yes, VN and VP, right? One second. Yeah. So VN and VP, the comparison is done. So what will you do? You will, oh, sorry. Let's give a signal in this way, positive, negative, right? So this is the, please mind it, this is positive, this is negative, according to my voltage source. So I give a VE, error voltage here, right? Now tell me, what will be the voltage at the output? And by the way, I should not be disconnecting it, right? I give an error voltage here. I do what? This has to be connected here like this, right? Yes. I give an error voltage here. What will be the output here? Let's say the gain is some A. At later
A,
stage, we will say it is A is equal to infinity. So what will be the voltage here? V0 is equal to
A
A
times
into V.
A into
hmm,
V.
V0 is equal to A into V E, right?
V.
And yeah, so what will be the voltage here?
So that will be AV.
AVE, right? Plus AVE. Please let's keep also noting the signs, okay? And what will be the voltage here?
Um, so that will be 3 by 3 by 5 AV.
Okay, right? And so what is it that returns? So I gave an input which is VE, right? The place where comparison was done. What is returning to this place?
Um, minus 2 by 5
Exactly. You
AV.
have to do the subtraction, by the way, right? You have to do the subtraction. And which way you have to do the subtraction? Tell me.
So the one that we gave at the input, right? So the same one
Same
will
sense,
see
right?
up.
Because I
Yes.
have assigned this to be positive, this to be negative here. Same way, I should also take the difference also, right?
Yes.
Yes. So I should take VP minus VN. And what is VP minus VN? It is? minus 2 by 5 a times b, right?
Yes.
Yes. So
Yes.
in response to the input that I gave, in response to the error input that I gave, the feedback is making sure that the response of this error is coming out to be a negative. I mean the response is coming out to be opposite of the sense of what I fed it, right? Which is a classic recipe of negative feedback, isn't it? It's a telltale sign of negative feedback that whatever input that I gave, whatever error I injected in at the in the loop, the error that I injected in the loop at some place, what is happening? The loop is making sure that the response of the loop is exactly opposite of that particular disturbance, right? The loop is making sure that the response to that particular disturbance is opposite in sense to the direction in which I disturbed it, right? So that is the classic sign of negative feedback. So this is what? This is negative feedback, isn't it?
Um,
Correct?
yes.
Okay. So
So so
now that you understood what is
Negative or positive feedback. Now I hope you will be able to do another question which is exactly similar to this, just that they have a current source here. Yes, Ravi.
so like we established the sense of negative feedback over here, or similarly we'll establish for positive for any other
Yeah,
system.
had this system had this response been plus 2 by 5, it would have become a positive feedback. Once the system is in positive feedback, you can no longer say that Vn is equal to Vp. That is not guaranteed. Okay.
Hmm.
Okay.
So you spoke about the importance of the loop gain. Is this the importance of the loop gain in a sense, or
Loop gain sign matters in this case. The loop gain the value of loop gain, how large it is, that significance is basically in the that has its importance in the effectiveness of the loop. How effective is the loop? If the loop gain is very large, then the loop will be very effective in controlling. Okay, it's just like I will tell you a very if you have just give me just 5 minutes, I will give you a very small analogy. We'll be able to understand it. Let's say you have a child. Okay, let's say you have a child. Now now that child is very small. I mean, let's say he or she is in second class or third standard or fourth standard, whatever. And let's say that child is really really stubborn, kind of. Let's say stubborn. Let's say it's a very stubborn child. Okay, and let's say you want to teach him or her maths or whatever, this electronics only. No, let's talk about maths. You want to teach that child maths. Now that child is very stubborn, but it will learn whatever you will teach that child. That child will learn whatever you will teach him or her. Okay, now you want to teach him or her maths, right? But that child is very stubborn minded. So tell me something. uh, how effective will that? I mean, if you let's say you give that child a chapter to learn, and if you just leave that child, and do not say anything to that child, what do you think that child will do? Will that child ever learn maths?
no?
No, it will not learn. Now let's say another example. You have it's your wife, okay? No, not wife. Let's say you only. What you do is you understood that, okay, if I do nothing, it will not that child will not learn. So what you did is you said, okay, I will maybe invigilate his learning, or invigilate him or her, and make him or her learn 2 hours a day, right? You want to make him or her learn 2 hours a day properly, but not with very strict this thing, not with very strict discipline. You just stay there so that you just see whether that child is learning or not. And because of that, that child is learning a little bit. So now that child is learning a little bit. Now a third case is when you are very strict with that child, okay, and minded that child is kind of like a robot, okay, and it will learn whatever you will teach. So this child is like a robot, and now you are very strict with that child. You are sitting like 8 hours a day with that child. Okay. Now tell me, in which case will the child learn faster and in a much more effective manner?
Yeah, the last situation.
Large situation, right? Which means that
Yes.
the more power you exert on that child, the more influence you have on that child, the faster and the better effect with more effectiveness that child will learn, right?
Yes.
Same is the case with negative feedback also. The more control, the more powerful control the system has in its controller, the more effective will be the control. So that controller power is that control effectiveness comes from the term here. Okay, that is the loop gain. Okay, that is the loop gain. How powerful is that error signal being that is being circulated in the loop? If that error if that error that is generated, and then the loop gain is very large, which means what? A lot of that power, lot of that error is coming back to it. Okay, think of it like a lot of the bad things that the system has done, it's coming back to it for it to look back and correct it. Think of it in that manner.
Um,
Okay.
yeah, I mean, I get your point, but one scenario can also be, let's say if we have a very large loop gain,
Uh,
then when it comes back, the value can be so large. So when it is integrated at the output, it can oscillate, right, to large values. Ultimately, it will die down, but for the transient case, we'll have very large oscillations. Can it be with a large?
no, that happens when you have delay in the system. Okay, yes, exactly. So that exactly is the case. If you have a delay in the system, then if you have a very large gain, yes, then you are very then there is a real chance of being oscillate being you getting into oscillations. Okay, but if there is no delay, please understand that if the system has no delay at all, whatever you do, it comes back to you immediately for you to correct. Then you do not have any problem like that. Okay, then you do not have oscillation. What you are thinking is exactly the case that happens when you have a delay in the system. In fact, when you have a delay in the system, you will have to some way reduce the gain of the system somewhere. Okay, to make sure that the system is stable.
Okay, great, got
Okay,
it. Thank you.
right.
Yes.
That is what is going to come later in when we talk about stabilizing the system. When you have a delay, you create compensation and all, and compensation does nothing but it makes sure that the
Gain is reduced at places where the system has the chances of becoming unstable. Okay, that is exactly what is done. So yeah, anyway, so this is now since this is understood, so now to summarize, what you have to do when you have to find out the sense of negative feedback, you simply have to break the loop. Okay, you simply have to break the loop. So here, what did we do? Where did we break the loop here? We broke the loop at this point, right? We broke the loop at this point. You have to break the loop at this point, and then after breaking, at one side you have to apply a voltage like this. Okay, and at the same place, at the other side of this or at the place where you broke the loop, you have to check what is the sign of the signal that comes back because of the input that you applied. Is that understood?
Yes.
And in doing so, you have to first make sure that all the independent voltage sources and current sources are nullified. Please mind it, independent. Okay, independent only. The dependent sources you cannot nullify. All the independent sources all the independent voltage and current sources you have to nullify. Okay, so because I explained this, I am sure that you will be able to understand. You will be able to do the second question also in this, and in fact, the first question also you have to do finish everything. I also talked about the power, how to calculate power delivered or power dissipated in an element. I talked about the passive sign convention, which was explained here. With this, I think you'll be able to solve all the question in the assignment. Okay. I have not solved any question which I wanted to discuss in this particular week. It's okay. Let's anyway. I'll be posting all these questions for you to solve. Please solve them. Okay. If you have any doubt, I will discuss this in the next class. If you do not have any doubt, I will think that you have attempted and just solved them all. I'll not discuss it if you do not have any doubt. Okay. So thank you for joining everyone. We'll meet again next week. the same time, 6 to 8, Monday. Okay.
Okay.
Thank you. Thank you very
Thank you.
much.
Thank you.